Boom! All right, Julie, welcome to Capacitors. Yeah, we're in chapter 5 right now. We're making quite some progress. In chapter 5, we're going to be discussing capacitors. Remember, in the previous chapter, we talked about electrical potentials, okay? And we saw that there were two types, electrical potential energy and electrical potential itself, right? All right, so but now we are focusing on capacitors. First, what is a capacitor? A capacitor consists of two parallel plates of the same size, same shape, separated by a distance, usually with an insulator inside. At times you may not find an insulator within, you know. So, and the plates of a capacitor are usually equal. And basically, this device is used to store charges. That is the job of a capacitor, basically as a charge storage device. Now, it is important for you to know that capacitor plates, although they are equal in size, equal in quantity of charge, however, they are different when it comes to potential difference. That's a little bit contradictory, right? They have the same quantity of charge, they have the same plate size, they have everything equal, but in every capacitor, the parallel plates to each other are of different electrical potential. That is to say, one plate has a higher potential difference than the other, even though they have the same size and the same quantity of charge. One of them has a higher voltage than the other. So the one that has a higher voltage is always the one connected to the positive terminal of the battery. While the one with the lower voltage is the one connected to the negative terminal of the battery. Now, ideally, a capacitor plate comes with the same capacitance in terms of quantity of charge, in terms of size. By the time you take positive plates and give to one of them and take negative terminal and give to the other one, just know that the one that you give the positive terminal of the battery will have a higher potential difference. Why? Because positive terminal radiates their field line outward. Electric current will move from the positive charge into the other side. So it will accumulate more potential difference than the negative. That's what we're trying to say. So they are of different potentials. Now, having known that a capacitor is actually a storage device, what are the different types of capacitors that we have? We have basically four capacitors. Number one, the leading jar capacitor. Number two, the fixed capacitor. Three, variable capacitor. And four, electrolytic capacitors. Now, each of these capacitors have their applications. They have where they are useful. Let's start with the first guy, leading jar capacitor, aka the covenant box in the olden days that struck someone dead. Science has made us to understand that that covenant box was a leading jar capacitor. But that's science anyway. They have their own point of view. Now, what is a leading jar capacitor? It consists of two coated sheets of glass vessels. That means the glass is a glass vessel coated in and out. The inside is coated, the outside is as well coated. It has a knob, that sinks into the glass vessel, and that knob is negatively charged knob into the glass vessel, while the body of that glass vessel of the jar is positively charged, right? Good. Now, if you want to charge this particular leading jar capacitor, all you need to do is to connect the knob and the body of the leading jar capacitor to a source of power. It will charge it. If you want to disconnect it, you still connect the knob, which is negatively charged, and the body of the leading jar capacitor, which is positively charged. Connect it to a bulb or a DC device, and it will power it and discharges it. So once it gets discharged, you can power it again. So that is a leading jar capacitor. Some cases it comes with oil between the two coated. Some cases it comes with oil between the two glass material that act as an insulating surface or something. So just know that the same point where you use to power is the same point you use to discharge, right? So what are the uses of a leading jar capacitor? A leading jar capacitor is purely used in demonstrations and widely used in radios and television sets and other electrical and electronic equipment. So basically demonstration purpose. They are also used in radio and TV sets, but those are the olden days radios and TV sets. Now that takes us to the fixed capacitor. From the word fixed capacitor, they have fixed capacitance. It's either 100 farads, 50 farad, 10 farad, 10 microfarad, 100 microfarad. Fixed. You can use above, you can use below. So it is a fixed capacitor. So they are not adjustable, and they are just what they are. And they are mostly used in wireless devices. However, they are very cheap. You can just find a 50 microfarad capacitor, they tell it's 20 naira. That's crazy, bro. But that's the gospel truth, very cheap. And they are just fixed. As for the variable capacitor, they are adjustable. They have variable capacitance, which means you can adjust them to the size of the capacitance you want to use. It can come rated 100 microfarad. You can decide to use 50 by adjusting the plates. Now, what plates do you adjust? You adjust the set of semicircular plates that are separated by air or oil as dielectric. The semicircular plates are made of brass or aluminum. So by the time you adjust, by the time you tune, by turning it clockwise or anti-clockwise, it increases the surface area of the plate or decreases the surface area of the plate so as to either increase capacitance or reduce capacitance. Remember, increase in area increases capacitance, isn't it? Decrease in area decreases capacitance because capacitance is directly proportional to area, but inversely proportional to the separation distance between them, right? Good. So where do you find variable capacitors useful? Number one, they are very, very useful in setting resonance frequency in LC circuit. Very useful in setting resonance frequency, where inductive reactance happens to be equal to capacitive reactance. That's resonance. They are very useful in that area. They are also useful in tuning radios, tuning control in radios and antennas. That's where you find variable capacitors very pertinent. Now that takes us to the last guy, which is the electrolytic capacitors. Electrolytic capacitors are very similar to fixed capacitors. It consists of two long aluminum foils separated by a cotton material called muslin. When the terminals of these capacitors are connected to a DC battery, a thin coat of aluminum oxide is formed at the anode, which serves as a dielectric. That means once you connect it to a DC battery supplier or a DC voltage supplier, a thin coat of aluminum oxide is formed at the anode. And this thin aluminum oxide produced serves as a dielectric material because it does not conduct. Now, the advantage of this capacitor is that it produces a very large amount of capacitance due to the formation of aluminum oxide. The aluminum oxide form when a DC circuit is connected to it. The aluminum oxide form when a DC circuit is connected to it increases capacitance because it acts as a dielectric that multiplies the capacitance of the capacitor. And then it is very important for you to know that in as much as it is very useful in generating high capacitance as a result of the formation of aluminum oxide, it can be very deadly and detrimental, especially when you mismatch the terminals. It can explode, it can catch fire, it can cause death. It is that bad. However, where do you find this capacitor very useful? It is useful in noise filtration. Very, very pertinent. It is very, very useful in noise filtration. So that takes us to the next part. We are done with the types of capacitors. Now you know leading jar, fixed, variable, and electrolytic capacitor. So now we go into the full concept of capacitor itself. Good. First, you have to understand that when you take the two terminals of a capacitor and connect to a DC supply, that is a voltage supply, the amount of voltage produced is directly proportional to the quantity of charge generated in the process. So V is directly proportional to what? V is directly proportional to charge at constant capacitance. So on that note, you will have Q to be equal to CV. And once you have Q as CV, that is a product of capacitance and potential difference. That formula is sacrosanct. Number two thing you must note here is that the capacitance of a capacitor is directly proportional to the cross-sectional area of the plates of the capacitor, but inversely proportional to the separation distance existing between the plates of the capacitor. You get it? Good. If you don't get it, forget about it. And of course, you can derive this formula using Gauss' law that says that flux is equal to Q all over epsilon naught. Change E there as change the flux there as EA. That E you have, change it to V over R because you're actually looking for capacitance. So if E is V over R or V Then V becomes ER, which is ED as the case may be. And if V happens to be ED, and you know that capacitance is quantity of charge over V, then substitute your V and then boom, you get back to the equation. So C becomes E naught A over D. Good. Also take note that there is a relationship between potential difference, electric field, and distance between the plates of a capacitor. So V is equal to ED. Very, very important. And then also take note of these parameters, although they may look a little bit confusing, but you need them very well. Number one, the capacitance of a coaxial cylindrical capacitor. When you talk about a coaxial cylindrical, they have a common axis. They have a common center. A coaxial cylindrical capacitor has a common center. So there are actually two capacitors. The inside one is positive, the outside one is negative, and then you have a Gaussian cylindrical surface around it. So what we are saying is that the capacitance of a coaxial cylindrical capacitor is given by C equals to 2 pi L epsilon naught all over lane B over A. The L is the length of the cylindrical capacitor. The L is the cylindrical capacitor, which is actually circumference, right? Good. Next is the A you see there is the radius of the internal capacitor. B is the radius of the external capacitor. The radius of the internal capacitor is always less than the radius of the external, while the radius of the external is less than the radius of the cylindrical capacitor. You have to be very careful with those parameters because they are sacrosanct. Next, the capacitance of an isolated conducting sphere capacitor. Take note, the capacitance of an isolated sphere conducting capacitor whose radius is A is given by 4 pi epsilon naught A. A is the radius, or you can simply say 4 pi R epsilon naught. And this same capacitance is equal to the capacitance of a concentric sphere capacitor, which is 4 pi epsilon naught A, or 4 pi R epsilon naught. Now, you may be wondering how this formula came about. Gospel truth, you don't need it. But if you want to derive it, I will teach you through the processes of derivation. But just know that C is equal to 4 pi epsilon naught A. Then, let's assume that I should just explain this particular one for you. V is equal to ED, right? Good. E is equal to KQ over R squared. Electric field intensity, right? Substitute that in that equation, and then you come up with KQ over D as your V. Good. If I have V as KQ over D, and I know that C is quantity of charge per voltage, I will just substitute my voltage at the bottom of my C, which is Q over V, and then make my C the subject of the formula. And of course, having substituted that, I will change my K to 1 over 4 pi epsilon naught. Cancel out parameters where necessary, and boom, you have 4 pi A epsilon naught. That A there will take the position of D. You get it? If you don't get it, forget about it. Next, that takes us to the 4 basic parameters, or the 4 basic factors that affects the capacitance of a capacitor. Number 1, the area of the plate, which is directly proportional. Number 2, the thickness of the dielectric material, which is also directly proportional. Number 3, the distance between the plates. The distance between the plates, which is an inverse proportionality. And then number 4, the geometry of the plate. Yeah, the geometry of the plate is key. Not all shapes will store the same capacitors. Remember, the pointed end, the pointed edge of every object that is conducting is the edge where more charges are concentrated, right? Good. Now that takes us to capacitors in series and in parallel. There is one amazing thing you need to know about capacitors in series and capacitors in parallel. Remember UIQ. UIQ are always the same in series and in parallel. It's either they are same or they are algebraic sum. Just remember UIQ. Then VC will always vary. V is the voltage, C will always vary, depending on whether they are in series or in parallel. So we start with the first guy there, which is series arrangement. Assuming I have 3 capacitors arranged in series, C1, C2, C3, with their voltages V1, V2, V3, and then of course a current flowing through them, I1, I2, I3, stuff like that. And then the quantity of energy stored, which is U now, energy stored, U1, U2, U3, and then some potential questions are asked. What is the effective capacitance when they're in series? Effective capacitance is simply the reciprocal sum of the capacitors. That's 1 over C effective equals to 1 over C1 plus 1 over C2 plus 1 over C3. You got it? Take note, 1 over C1 plus C2 can also be written as C2 plus C1. So C1, C2 divided by C1 plus C2. But you can't do that for C3, for N3, because it is complex. But your textbook actually said it works, but that's a mistake. So you can correct that for students anytime you listen to this audio. So the complexity starts from N equals 3 when you have 3 capacitors, right? So first, capacitance is the reciprocal sum. Now, what about potential difference? Potential difference in series arrangement is the algebraic sum. Yes, the voltage in the first capacitor is not equal to the voltage in the second, it's not equal to voltage in the third. Remember CV, the vary. Good. Now, what about quantity of charge? Quantity of charge is the same. Current is the same. Energy stored in each capacitor is the same. QIC. Sorry, QUIQ as the case may be, or QIU. Very, very important. So that takes us to parallel arrangement. In a parallel arrangement, current will split into I1, I2, I3. And current is not the same. And once current is not the same, quantity of charge can never be the same. And once quantity of charge is not the same, energy stored is not the same. And this happens in a parallel arrangement. Now, what happens to capacitance and voltage? Capacitance becomes algebraic sum when it is in parallel. As for voltage, voltage becomes equal. So that's the best way to remember them. And it is pretty simple in its dimensions. Next, so when we talk about current in parallel, you talk about algebraic sum. Quantity of charge in a parallel, algebraic sum. Energy stored in parallel, algebraic sum. But as for series, they are the same. Good. Now that takes us to the amount of electrical energy stored in a capacitor. The amount of electrical energy stored in a capacitor is dependent on the potential difference applied in the capacitor. In other words, the work done in charging the capacitor is directly proportional to the potential difference passed through the capacitor. So work done is directly proportional to VQ. And then you know that V is equal to Q all over C. So substitute your V to be Q all over C, then integrate Q all over C dQ. And when you do that, you will end up having Q squared all over 2C. And when you say that C is equal to Q all over V, you get a new formula, which is a half CV squared. And when you say that C is equal to Q all over V, again, you have a new formula, which is a half QV. However, there are 3 formulas for energy stored in a capacitor. Number 1, a half QV. Number 2, let your Q be CV. You will have a half CV squared. Number 3, let your V be QC. You will have Q squared over 2C. These are the energies stored in a capacitor. But if you can't remember this very well, if you can't remember the concept of a half QV, remember that the work done is directly proportional to the potential difference and the quantity of charge stored. So work done equals V over Q. And from there you can solve and get the energy stored Joule's effect. So that takes us to energy density represented by U. Energy density is the energy stored per unit volume of a parallel plate capacitor. Energy stored per unit volume of a parallel plate capacitor is called energy density. And I want to draw your attention to the relationship between energy density and electric field. Energy density, which is the energy stored per unit volume, is directly proportional to the square of electric field, where the constant of proportionality is epsilon naught over 2. And in cases where you are asked a relationship between energy stored and electric field, just know that U is directly proportional to E squared. And you can have your E1, U1, E2, U2 as the case may be. You get it? If you don't get it, forget about it. So electric field, you can always make it a subject of the formula when asked. Fringing effect. I won't stop this step without telling you what fringing effect is. What is fringing effect? Fringing effect occurs as a result of the presence of air bubbles within a dielectric material. inside capacitor plates. The presence of these air bubbles actually results to irregularity in flux density, and as a result of the irregularities in flux density within the dielectric material, then you discover that your capacitor starts misbehaving. So fringing effect occurs due to the presence of air gap or air bubbles between the plates of a capacitor. And at times it can also happen within dielectric materials. Good. So that is the end of capacitors. In our next step, we're going to be discussing dielectric. And dielectric in itself is another amazing topic which you would not like to miss. See you in the next chapter, bro. Boom.